Article 230.90 does not apply to overcurrent protection of service entrance conductors. Article 230.82 requires that service entrance conductors shall be not smaller than those required by Article 220. Article 220.42 requires that a continuous load of 1500 amps to have 500 MCM or greater conductors. Article 220.10 allows you to have 125% of the continuous load on a conductor. This means that 1520 amps is the maximum continuous load on these conductors. If there was to be an addition, then the service equipment would have to be upgraded to a 2500 amp service to meet the 125% of the continuous load requirement. Let's break this down further. The initial setup involves a 2000 amp, 3-phase, 480 volts main switch intended to be fed by 4 sets of 500 MCM copper conductors from the utility company's transformer. The calculated loads are 1500 amps in accordance with NEC Articles 220 and 230.42. 4 sets of 500 MCM copper conductors are rated for 1520 amps at 75 degrees Celsius. The question revolves around whether Article 230.90 or any other relevant article applies to the overcurrent protection of these service entrance conductors. Firstly, understanding the role of Article 230.90 is crucial. This section of the National Electrical Code primarily addresses the overcurrent protection of service entrance conductors. However, it's important to note that Article 230.90 doesn't directly dictate the sizing or protection of the service entrance conductors themselves. Instead, it focuses on the service disconnecting means and its overcurrent protection. Secondly, Article 230.82 plays a significant role. This article mandates that service entrance conductors must be sized no smaller than what is required by Article 220. Article 220 deals with the calculation of branch circuit, feeder, and service loads. This means the conductors must be adequately sized to handle the calculated load, ensuring safety and preventing overheating. Thirdly, Article 220.42 directly addresses the sizing of conductors based on continuous loads. In this scenario, a continuous load of 1500 amps necessitates the use of 500 MCM or larger conductors. This requirement ensures that the conductors can safely carry the sustained load without exceeding their ampacity. The ampacity of a conductor refers to its current carrying capacity under specific conditions without exceeding its temperature rating. Fourthly, Article 220.10 introduces the concept of A-line conductors to be loaded up to 125% of the continuous load rating. This is a critical aspect of electrical design because it accounts for situations where loads are expected to operate continuously for extended periods. In this case, with the conductors rated for 1520 amps, the maximum continuous load they can handle is indeed 1520 amps. This is because 1520 amps represents 125% of the continuous load, which is 1216 amps. It is important to never exceed the rated ampacity of the conductors. So if an additional piece of equipment is added, then that could change everything. If an additional load is added, the existing service equipment may need to be upgraded to accommodate the increased demand. Let's consider the scenario where the total calculated continuous load exceeds the existing service capacity. To meet the 125% requirement of Article 220.10, the service equipment would need to be upgraded to a 2500 amp service. This upgrade would ensure that the conductors and overcurrent protection devices are adequately sized to handle the increased load safely and effectively. The decision to upgrade to a 2500 amp service is based on the need to maintain compliance with the NEC and to ensure the safety and reliability of the electrical system. Failure to do so could result in overheating of conductors, premature equipment failure, and potentially hazardous conditions. In this specific scenario presented, with 4 sets of 500 MCM copper conductors rated for 1520 amps, it's essential to adhere to these guidelines to prevent overloading and ensure compliance with the NEC. The ampacity of conductors is influenced by factors such as conductor material, insulation type, ambient temperature, and the number of conductors bundled together. Copper conductors typically have higher ampacity ratings compared to aluminum conductors of the same size. This is because copper has lower electrical resistance, allowing it to carry more current without overheating. The insulation type of a conductor also affects its ampacity rating. Different insulation materials have different temperature ratings, which determine the maximum temperature the conductor can withstand without degrading the insulation. Common insulation types include THHN, THWN, and XHHW, each with its own temperature rating and application. Ambient temperature plays a crucial role in determining the ampacity of conductors. Higher ambient temperatures can reduce the ampacity of conductors, as the heat generated by the current flow is dissipated less efficiently. Correction factors are applied to conductor ampacity ratings to account for variations in ambient temperature. The National Electrical Code provides tables that list ampacity correction factors for different temperature ranges. The number of conductors bundled together in a raceway or cable can also affect their ampacity. When multiple conductors are bundled together, the heat generated by each conductor can raise the temperature of the surrounding conductors, reducing their ampacity. Dating factors are applied to conductor ampacity ratings to account for the number of conductors bundled together. The NEC provides tables that list ampacity dating factors for different numbers of conductors. Overcurrent protection is a critical aspect of electrical safety, designed to protect conductors and equipment from excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent condition is detected. Fuses are overcurrent protection devices that contain a fusible link that melts and breaks the circuit when an overcurrent condition occurs. The selection of appropriate overcurrent protection devices is crucial to ensure the safety and reliability of the electrical system. The overcurrent protection device must be sized to protect the conductors and equipment it serves, while also allowing for normal operating currents. The NEC provides guidelines for selecting overcurrent protection devices based on the ampacity of the conductors and the characteristics of the equipment being protected. Article 220 provides comprehensive guidelines for calculating branch circuit, feeder, and service loads. These calculations are essential for determining the appropriate size of conductors and overcurrent protection devices. The load calculations take into account various factors, such as the type of occupancy, the square footage of the building, and the types of electrical equipment being used. The NEC provides tables and formulas for calculating the demand factors for different types of loads. Demand factors are used to reduce the calculated load to account for the fact that not all electrical equipment will be operating at its maximum capacity simultaneously. Continuous loads are loads that are expected to operate continuously for 3 hours or more. The NEC requires that conductors and overcurrent protection devices be sized to handle 125% of the continuous load. This requirement is intended to prevent overheating of conductors and equipment due to prolonged operation at high current levels. Non-continuous loads are loads that are not expected to operate continuously for 3 hours or more. Conductors and overcurrent protection devices are sized to handle 100% of the non-continuous load. Understanding the difference between continuous and non-continuous loads is essential for accurate load calculations and proper sizing of electrical equipment. The service entrance conductors are the conductors that run from the utility company's transformer to the service disconnecting means. The service disconnecting means is the main switch or circuit breaker that disconnects the building's electrical system from the utility company's power supply. The NEC provides specific requirements for the size and installation of service entrance conductors and service disconnecting means. These requirements are intended to ensure the safety and reliability of the electrical system. The grounding system is an essential part of the electrical system, designed to provide a low impedance path for fault currents to return to the source. The grounding system helps to prevent electric shock hazards and to protect equipment from damage due to ground faults. The NEC provides detailed requirements for the design and installation of grounding systems. These requirements cover various aspects of grounding, such as grounding electrodes, grounding conductors, and equipment grounding. Proper grounding is essential for the safety and reliability of the electrical system. Bonding is the process of connecting metallic parts of the electrical system together to create a low impedance path for fault currents. Bonding helps to prevent voltage differences between metallic parts, which can create electric shock hazards. The NEC provides specific requirements for bonding different parts of the electrical system, such as metal raceways, equipment enclosures, and grounding electrodes. Proper bonding is essential for the safety of personnel and the protection of equipment. The National Electrical Code is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment. The NEC is updated every 3 years to reflect changes in technology and best practices. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. Electrical inspections are conducted to verify that electrical installations comply with the NEC and other applicable standards. Electrical inspectors are trained and certified to identify electrical hazards and to ensure that electrical systems are installed correctly. Electrical inspections are an important part of the electrical safety process. Electrical safety is paramount in any electrical installation or maintenance activity. Working with electricity can be dangerous, and it is essential to take precautions to prevent electric shock and other hazards. Always to energize electrical circuits before working on them. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow safe work practices and consult with qualified electrical professionals when necessary. Continuous load calculations are essential for determining the appropriate size of conductors and overcurrent protection devices. When calculating continuous loads, it is important to consider all loads that are expected to operate continuously for 3 hours or more. This includes lighting, 8-track equipment, and other appliances. The NEC requires that conductors and overcurrent protection devices be sized to handle 125% of the continuous load. Demand factors are used to reduce the calculated load to account for the fact that not all electrical equipment will be operating at its maximum capacity simultaneously. The NEC provides tables and formulas for calculating the demand factors for different types of loads. Demand factors can vary depending on the type of occupancy, the size of the building, and the types of electrical equipment being used. The service disconnecting means is the main switch or circuit breaker that disconnects the building's electrical system from the utility company's power supply. The service disconnecting means must be readily accessible and capable of disconnecting all ungrounded conductors simultaneously. The NEC provides specific requirements for the location and rating of the service disconnecting means. The grounding electrode system is a network of interconnected grounding electrodes that provide a low impedance path for fault currents to return to the source. The grounding electrode system typically includes grounding rods, ground rings, and metal water pipes. The NEC provides detailed requirements for the design and installation of grounding electrode systems. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding system. Equipment grounding conductors provide a low impedance path for fault currents to return to the source, helping to prevent electric shock hazards. The NEC provides specific requirements for the size and installation of equipment grounding conductors. Bonding jumpers are used to connect metallic parts of the electrical system together to create a low impedance path for fault currents. Bonding jumpers are commonly used to bond metal raceways, equipment enclosures, and grounding electrodes. The NEC provides specific requirements for the size and installation of bonding jumpers. Overcurrent protection devices are designed to protect conductors and equipment from excessive current flow. Circuit breakers and fuses are the most common types of overcurrent protection devices. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent condition is detected. Fuses are overcurrent protection devices that contain a fusible link that melts and breaks the circuit when an overcurrent condition occurs. Short circuit protection is designed to protect the electrical system from damage due to short circuits. Short circuits occur when there is an unintended connection between two or more conductors, resulting in a high current flow. Overcurrent protection devices, such as circuit breakers and fuses, are used to interrupt the flow of current during a short circuit. Ground fault protection is designed to protect personnel from electric shock hazards caused by ground faults. Ground faults occur when there is an unintended connection between a conductor and the ground, resulting in current flowing through the grounding system. Ground fault circuit interrupters, GFCIs, are used to detect ground faults and to interrupt the flow of current before it can cause harm. Surge protection is designed to protect electrical equipment from damage due to voltage surges. Voltage surges are sudden increases in voltage that can damage sensitive electronic equipment. Surge protected devices, SPDs, are used to divert surge current away from the equipment and into the grounding system. Electrical panels are enclosures that house circuit breakers and other electrical components. Electrical panels provide a convenient location for distributing electrical power throughout the building. The NEC provides specific requirements for the location, installation, and labeling of electrical panels. Conductors are used to carry electrical current from one point to another. Conductors are typically made of copper or aluminum. The NEC provides specific requirements for the size, type, and installation of conductors. Cables are assemblies of two or more conductors enclosed in a protective jacket. Cables are commonly used for branch circuit wiring and for connecting electrical equipment. The NEC provides specific requirements for the type and installation of cables. Raceways are enclosed channels that are used to protect and support electrical conductors. Conduits, tubing, and cable trays are common types of raceways. The NEC provides specific requirements for the type and installation of raceways. Electrical boxes are enclosures that are used to terminate and protect electrical connections. Electrical boxes are commonly used for switches, receptacles, and lighting fixtures. The NEC provides specific requirements for the type and installation of electrical boxes. Lighting fixtures are devices that are used to provide illumination. Lighting fixtures are available in a wide variety of styles and types. The NEC provides specific requirements for the installation and wiring of lighting fixtures. Switches are devices that are used to control the flow of electrical current. Switches are commonly used to turn lights and appliances on and off. The NEC provides specific requirements for the installation and wiring of switches. Receptacles are devices that are used to provide a convenient point of connection for electrical appliances. Receptacles are commonly known as outlets. The NEC provides specific requirements for the installation and wiring of receptacles. Appliances are electrical devices that are used to perform a specific function. Appliances include refrigerators, washing machines, and dishwashers. The NEC provides specific requirements for the wiring and installation of appliances. Motors are electrical devices that are used to convert electrical energy into mechanical energy. Motors are used in a wide variety of applications, such as pumps, fans, and compressors. The NEC provides specific requirements for the wiring and installation of motors. Transformers are electrical devices that are used to change the voltage of electrical power. Transformers are commonly used to step down voltage for use in residential and commercial buildings. The NEC provides specific requirements for the installation and wiring of transformers. Generators are electrical devices that are used to generate electrical power. Generators are commonly used as backup power sources during power outages. The NEC provides specific requirements for the installation and wiring of generators. Batteries are devices that are used to store electrical energy. Batteries are commonly used in portable electronic devices and in uninterruptible power supplies. The NEC provides specific requirements for the installation and wiring of batteries. Renewable energy systems are systems that generate electricity from renewable sources such as solar, wind, and hydropower. The NEC provides specific requirements for the installation and wiring of renewable energy systems. Electrical safety is essential for preventing electric shock and other hazards. Always to energize electrical circuits before working on them. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow safe work practices and consult with qualified electrical professionals when necessary. The information provided here is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific electrical design and installation requirements.